right, in the last video, we defined the intersection, we defined the union, and we defined the sum for any x and y inside a vector space. All right, so we want to get a feeling for what this is happening, and really we have a question in mind in the back of our head. We want to know that what happens if x and y are subspaces. If x and y are subspaces of vector space, I want to know which ones of the intersection, the union, and the sum are still subspaces of Z. So let's start with an example. We'll see what works and what doesn't work in that case, and then we'll try to prove that what worked in that case works in general. Oh, sorry. All right, so I want to start with Z equals E3, the Euclidean vector space of dimension 3. So that means 3D vectors with the regular sum and regular scalar multiplication. I'm going to look at x, which is this vector space, and I'm looking at y, which is this vector space. First thing, show that x is a subspace, and I want to describe x geometrically. All right, so let's see. X is the set of all vectors that are t times 1, 0, 1 for t in R. You could prove the three properties. It wouldn't be long. In fact, we'll do it in the next section. We'll look at all spans, if you remember spans, and we'll talk about the fact that they're always subspaces. But here, just to save a bit of time and to make sure we're actually doing the work now and not putting it off for further, let's call it the solution set. Let's write it as a solution set. Here, x, I'm going to get t 0t. So I can get anything for x, but I'm going to have to find the same thing for z. And then y must be 0. All right, so that linear system will give me the solution set x. And so it's the solution set of x minus z equals 0 and y equals 0. And since this is homogeneous, by the theorem we just looked at, let's see, by the theorem of the last section, that's theorem 1.2.2. Let's just check. Theorem 1.2.2 that the solution space of any linear homogeneous linear system is a subspace. So X is a subspace. Now we're asked to describe it geometrically. Well, if you remember from linear 1, we get 0, 0, 0 plus t times 1, 0, 1. I'm adding a point just so you can recognize this is a line in R3 containing 0, 0, 0. So it contains the origin and passes by the origin, and it's parallel to 1, 0, 1. All right, let's do the same thing for y. So let me write it down. Y is the set t times 0, 1, 5. So very similar, just a different vector. I can do exactly the same thing. So this is the solution set of the linear system. X equals 0 and 5y equals z. And so that's the solution set of x equals 0, 5y minus z equals 0. This is a homogeneous system. It's a homogeneous linear system. And by theorem 1.2.2, y is a subspace. I can write it in the same way I wrote x in this last part. I can write it with the 0 point at the start. And so I'm going to get a line in R3 containing 0, 0, 0, the origin, and parallel to 0, 1, 5. All right, that does it. I want to find the intersection, and I'm going to show it's a subspace of Z. Well, we have two lines, and since 0, 1, 5 and 1, 0, 1 are not parallel, the lines are going to look like this. So here's the point that they start at. I have my green vector for, let's put it for x, and let me put a blue vector here. So that's 0, 1, 5 for y. All right, so the intersection, well, from the picture is pretty clear. You could do it algebraically as well, but whenever we have a chance to use geometry, I recommend it. It's so much nicer. All right, that's personal preference, of course. It's just a zero vector. Well, to show it's a subspace, you could prove the three properties. That's always an option, but we actually have done it before. So let's just use it. Where was it? Right here. Whatever vector space you have, if you take just the zero element, it's a subspace. And so that's what we've done here. So this intersection right here, it's a subspace. By example 1.2.5. All right, now we want to take the union and show that it isn't a subspace. All right, so the intersections seem to work. We'll prove it does always. The union usually doesn't work. I want to prove that here. So if I take the union, so the intersection was just this point, but if I take the union, I'm going to have to take all of the two lines, and so that's the union right here. All right, so I want to show that this isn't a subspace. This looks a lot like one of the examples we did, and so we'll treat it in the same way. I'm going to take 0, 1, 5, and I'm going to take 1, 0, 1. They're both in the union since one is in x and one is in y. And so here's what we'll do. All right, so I want to prove that property 2 doesn't hold, so I'm going to take v to be 1, 0, 1. V is in x, and so v is in x union y. I'm going to take w to be the generator, let's say, of y. So w is in y, and so w is in x union y. But now if I take the sum, so let's draw it as well. If I take the sum with the parallelogram rule, it's going to be this element. Sorry, this is a bit, there's too much going on right here. So let's draw the blue vector underneath. That was 1, 0, 1, 5. And so v plus w is going to be 1, 1, 6. V plus w isn't in x, because in x, if you remember, we needed, right here, we needed y to be 0. So here it's not in x as y equals 1 is not 0. V plus w isn't in y. For y, which one was it? In y, it was x that needed to be 0. But here x is equal to 1, which isn't 0. And so v plus w is not in x union y. And so property 3 does not hold. Let me make a tiny bit more room. So property 3 fails, which means that x union y is not. a subspace. All right, so for most example, X union Y will not be a subspace. In fact, property 2 in exactly this way is the one that's going to fail. You take an element that's in X, not in Y, an element that's in Y, not in X, and then you add them, and there's no reason it would land in X or in Y. And so the union will not be a subspace. That's the reason why we look at the sum. The sum is bigger than the union, but it's bigger because it needs to be a subspace. And so we add all the elements that we need because we need to be able to add this element with that one. And so we just take all the sums and that's going to work. All right, so let's do the last part. Give conditions on ABC that ensures that the vector ABC is in X plus Y and describe it geometrically. Show that X plus Y is a subspace of Z. All right, so I want, X plus Y, that's the set of something in X plus something in Y. And if you remember, X was T times 1, 0, 1. Let's put S so that, because they don't need to be the same parameter, so 0, 1, 5 for S and T and R. So really at this point, you might recognize this as a span. We'll actually consider spans in the next section. So at this point, either you choose to take the geometric approach or you take the algebra one. Whichever one you want will work. Let's do the geometric one. If you want in class, ask me and I'll do the algebraic one. It's nice too. And we'll do examples like this in the section on span anyways. So let's solve it geometrically. We're taking everything that looks like 0, 0, 0 plus T 1, 0, 1 plus S 0, 1, 5. And if you remember your linear 1, this is the vector equation of a plane. So it looks like this, where our two vectors, 0, 1, 5 and 1, 0, 1. And so the normal of that plane, hence the geometry, is 1, 0, 1, 0, 1, 5. Minus 1, minus 5, 1. And so we get minus x minus 5y plus z equals d, but up, of course, the point is 0, 0, 0, and so our d is 0. If we plug in 0, sorry, I mean 0, 0, 0. All right, so X union Y is a plane. Well, let's give the equation. It's the plane minus X minus 5Y plus Z equals 0. I asked for A, B, C because I was afraid that because we already had X, Y, and Z as set, it would be confusing. So let's write it as minus A minus 5B plus C equals 0. There's a time where you have so many letters that you run out of fresh letters. So it's a plane and it is a subspace because it's the solution set of a homogeneous system. And so X union Y is a subspace. All right, so in this, we kind of see that we have hope for the sum. The union will not work, but we have hope for the intersection. And so we'll see in the next theorem that that example was right. The intersection and the sum will always be subspaces, but the union is already out because of this example. So